in the evening. Okay, so thank you very much. So I will try to continue from what Carlo did, but in particular, what this second part, it's more about the covariant quantization of strings and bosonic strings and superstrings. So I will try to give you some methods, some technique to construct the quantization in a covariant way, namely respecting all the symmetries of the theory, namely constructing the quantization of the model where all the isometries or all the symmetries of the theory will be manifestly in the quantizations. So this means that well, probably you know it from other models, for example, like in Yamil's theory or other supersymmetric models. There are techniques where you can start from the theory, then you quantize it, and the quantization can be performed in a Hamiltonian way or other way, but in some sense this is good enough when you actually want to compute the spectrum of the theory. So you want to compute the spectrum, you need essentially the light cone or some non-covariant technique in order to distinguish what are the physical states. However, when you do some calculations, for example, when you really need to compute amplitudes or effective actions, in the case of string theory, usually you couple the theory to some background fields, then you do the calculation, and what you want to have is just an effective actions which is manifestly covariant, so namely respect all the symmetries which you expect to, namely, for example, Lorentz symmetry or even supersymmetry. However, this is generally rather difficult because in Yamil's or even in Maxwell theory, when you try to quantize the theory in such a way that you respect the Lorentz symmetry, you have to do something which is the following. So you know that on physical states you have a two polarization for Yamil's theory. Okay, so then you want to covariantize it. So this means two polarization is not an irreducible representation of the Lorentz group. You know that the minimal representation, the vector representation, contains at least 4 components. So therefore, you want to respect the Lorentz invariance, and you need 4 components of the Maxwell theory, of the Maxwell fields. Okay, so this means that 2 of the components are unphysical components. So one way is to quantize it in the light cone. So if you quantize in the light cone, you remove automatically these 2 states, and you end up in the light cone. However, when you construct the interacting theory and you construct diagrams, for example, you construct diagrams, of course, you start with light cone fields, okay? But then when you start to interacting with other fields, you can produce other fields in the loops, okay? So therefore, you really have to control in this process, I mean, in the quantization process, that the light cone condition, or namely the physical fields that you are really dealing with, are really propagating all in the loops. Okay. However, this is rather difficult to do it, okay, for several reasons. One of the reasons is the following. When you calculate the Feynman diagrams, okay, you really have to integrate on the full phase space, okay? So this means you have to integrate all the possible momenta of your amplitudes. See, this means you integrate over also on the momenta when P plus, which is just the light cone axis that you have chosen. So you have chosen, for example, that P plus is a constant and is different from 0. This is the way where when you quantize in light cone. So usually you define P plus, which is a constant and different from 0. Okay, this is just the condition. So then, when you integrate on the full phase space, okay, you certainly also encounter where P plus is going to be 0. And in that point, the light cone quantization that you have used so far, it does not work any longer. This happens also for string theory, namely, when you do calculation for string diagrams, at some point you encounter such a problem like a P plus different from 0. There is one way to overcome these problems, which is the following. Look, P plus is just P plus different from 0 is just a patch of your space. Okay, so your space of momenta, you can patch it by choosing, for example, P plus different from 0 in one patch, or another choice of light cone coordinate in another patch, and then you merge these two patches. And then you have to calculate all the transition function from one patch to the other patch. And this is rather difficult to do it. Okay, from some amplitude you can do it, okay? But the better way is try to do it in a covariant way. So you don't have to choose any light cone and try to do it in a covariant way. However, when you do in covariant way, of course, then the two additional degrees of freedoms that you added because you want to prospect the Lorentz symmetry start to propagating, okay? So then start propagating in the loops, start to propagating in the calculation, so you have those unphysical degrees of freedom all around. So you want to cancel them, okay? So in some sense, you want to have something which compensates the presence of these two unphysical fields, okay? The way to do it has been invented in the 60s, essentially, by Faddeev and Popov. Say you have to add some unphysical fields, okay, that actually cancel physically those two additional degrees of freedom. And okay, so you need the following. So you need the two fields, okay, at least in the case of Yang-Mills or in the case of Maxwell, you need the two fields actually, which they have essentially the same quantum numbers, but they have an opposite statistics. Okay, an opposite statistics means that the two fields, namely the two degrees of freedom you want to cancel, are bosonic degrees of freedom. So, namely, all the states that are generated by those fields are bosonic states, are cancelled by fields which has an opposite statistic. So they are fermionic fields. Okay. Now, there are several ways to do it, several ways to, let's say, to understand this process, okay? You can do it at the level of a Hilbert space. So the level of Hilbert space, you see that, for example, if you try to quantize the full gauge fields, okay, by preserving Lorentz invariance, you automatically end up with some fields that have wrong signs in the Hilbert space. So you have a negative norm states. In the same happen if you, example, you make you construct fields which have a wrong statistic. By spin statistic theorem, then automatically you find out that the Hilbert space that you constructed in this way has a wrong metric, a wrong norm, okay, namely a sign, a negative sign. In such a way, then you can combine these two ingredients in such a way that the physical product, physical scalar product in the Hilbert space turns out to be positive, okay, so you have only physical states. Okay, one way is to do it in this way. In the loops, it happens in the following. So when you construct the loops, now if you start from an H field, which contain all degrees of freedoms, then all degrees of freedom propagated inside of the loops, then you want to construct some loops of these unphysical fields, which actually compensate and cancel exactly those contributions. Now, of course, at the tree level, it's rather easy to see how the cancellation works. At one loop, well, one loop is almost like a tree level, so you can see it, let's say, by hands. But then when you start to have higher loops or interaction on different types, then it starts to become rather complicated how these let's say, how these unphysical fields do really cancel against let's say, how these unphysical fields cancel the unphysical degrees of freedoms, okay? So in the 60s, they invented this technique. So you introduce new fields. New fields. Usually they are called ghosts, okay? And they essentially have opposite statistics. Opposite statistics, okay? Namely, if the I want to cancel, okay, or if the degrees of freedom, okay, that I want to cancel are bosonic degrees of freedoms, I need some ghost which has fermionic statistics. If the fields, so the degrees of freedom that I want to cancel are fermionics, I need some commuting ghost fields. Okay, so the statistics of the ghost field is always opposite to the statistics of the fields whose degrees of freedom I want to cancel. Okay, so I will have some bosonic ghost. Bosonic ghost means some fields which have fermionic statistics and some fermionic ghost which has negative statistics, so they are bosonic fields. Okay. However, once I introduced the fields, I just half of the way, okay? Because I need to define what is the kinematics of those fields, interactions, okay, interactions, and of course I have to study, for example, if I have these new fields let's say for a field theory model, for example, I need to study, for example, the renormalization. The normalization in the case of renormalized quantum field theory, I need to study such a things. However, this is not, this is not an essential requirement. For example, for supergravity, okay, I will have some Gauss field. If I want to, let's say, to construct a propagator for supergravity fields, I need some Gauss fields. And for them, I will not care about renormalizability, but what I care is exactly how the interaction are built, how the kinematics of those fields are constructed, okay? So how to do all these things? So how to construct a formalism where all these things are considered, okay? And this is known today as the BRST formalisms. The BRST formalism. So the BRST formalisms actually allows me to construct the action for unphysical fields such a ghost. And it constructs observables. Of course, this is together related to the Hilbert space. A physical Hilbert space. Physical Hilbert space. S matrix. S matrix. Right, and let's say the covariant quantization of quantum field theories. So the covariant quantizations nowadays is obtained by using these BRST formalisms, okay? And in terms of the BRST formalisms, you actually achieve all these constructions, namely, you build up the action for those unphysical fields in such a way that the kinematics is fixed, in the way that the interaction are fixed, okay? You construct the Hilbert space, so namely you construct what are the physical fields and what are the physical states in your Hilbert space, okay? And then you construct the observable, so you construct the quantity that you can compute some correlation functions. S matrix is, of course, is an example of these observables, and of course this allows you to covariant quantize the theory. Namely, you can construct all these ingredients for a theory in such a way that you respect the symmetries, let's say the classical symmetry of your model. Okay. So the idea of these lectures, actually, it is starting from some very general framework, okay, to build up these BRST formalisms. So I will do it in the following way. First of all, I will give you some general remark. General remarks on BRST. Some, let's say, some ingredients that need in the future. So then I will apply to particles, and I will do it in two ways. One way is use what is known as word-line formalisms. Formalism, namely viewing a particle as really a material point moving on a line. Okay, and then I will show you with the same means, with the same technique, I will show you how to write down a target space action for these fields. Namely, this is okay. It seems rather trivial at this level, but it's. I mean, if you just add one more dimensions. Gosh. If you add one more dimension in this case, so we started with the word line here, but if you add one more dimension, so instead of one dimension, you have 1 plus 1 dimensions, okay, 1 time 1 space, then this becomes a worksheet, okay, you've seen in last lectures with Carlo, okay, and this becomes a worksheet formalism or either, let's say, string. And this, okay, the same technique I can use and build up a string field theory action. So here I have a model which is a word line. Here I built up a field theory model on this side. In the case of strings, I will start from strings and then I will build up a string field theory model, okay, using by the same technique. So, let's say the ingredient that I will give you, the instruments that I will give you, allows you to build up some string field theory models, starting from some word line or worksheet formalisms, okay. Then I will do it for superparticle. Superparticle in two ways, okay? Adding fermions on the worksheet or adding fermions in the target. Then we'll move to strings, really to strings. And then I will show you, so what are the ghosts? The BRC symmetry, the Hilbert space, then after that, again using the same framework, I will discuss strings, okay, not from a conformal field theory point of view, but more on the line of what Carlo did it in the last lectures, namely starting from mode expansion. So I will use the same expansion that Carlo already did it, but instead of using light cone, I will use just in a covariant way, okay. And then I will show you, for example, okay, how to build the Hilbert space, but then how to build from this construction the full partition function. The full partition function, which is actually, it is a generalization of what Carlo was discussing. In particular, I will construct what is known as the character. So a partition function which depends on Q, the modular parameter, but in addition it depends on some other parameter T, and this parameter T allows you to see all the states in your Hilbert space. This is rather beautiful because it allows you to count correctly the states in a covariant way. And then I will show you how the states are actually organized in multiplet, but not only the physical states, but even the unphysical states, and how the unphysical states give you the correct contribution in order to cancel these unphysical degrees of freedoms. Okay, this I will do it in this way, and then I will move to fermions. Okay, to fermions, and I will repeat what actually I did for superparticle. I will do it for superstrings. Okay, for superstrings. And for superstrings, I will need some super ghost fields. I will show you the BRC symmetry again, and then the Hilbert space, and in particular the Hilbert space, the full Hilbert space, again described using this character technique. Okay. Now, the first things I will do it in a formalism which is known as a Ramon-Schwarz formalism. And the Ramon-Schwarz formalism, it is the formalisms where you have some fermions on the worksheet. So it is a supersymmetrization of the theory on the worksheet. So you add some fermions, which are, and you add the supersymmetry on the worksheet, okay? And this gives you this technique, let's say this framework. However, this is not the only way. This is not a way. There is another sigma model which is called Green-Schwarz. Green-Schwarz formalisms, where actually you add some target space fermion. And then, okay, and the theory in this case is a supersymmetric in the target space. So the supersymmetry in this framework, it is just a supergravity on the worksheet. So it's a local supergravity in 2 dimensions, okay? And I think that Carlo showed you, for example, that you can construct a spectrum which is supersymmetric in the target space, okay? Here, it is manifestly supersymmetric in target space. So the spectrum will automatically give you a supersymmetric spectrum in the target space. However, this formalism, let's say, this framework of the Green-Schwarz can be only quantized as it is only in the light-cone gauge, okay? So I will go back again to light-cone gauge, okay? So in going back to light-cone gauge, I will show you some of the features of this model, but then, okay, I'll try to quantize it, okay? And the quantization of this framework gives you more recently a technique which is called pure spinor formalism, which actually preserve completely the supersymmetry and the Lorentz symmetry of the target space, but it gives you a way to quantize the theory in a, let's say, in a covariant fashion, and to compute all this ingredient, the BST symmetry, you compute the observables, you construct the Hilbert space, and so on and so forth, okay? And also for this, I don't know if I'm able to arrive to this point, also I'll give you the character formula for this framework, okay? Okay, so this is the plan of these lectures, okay? It is rather difficult to find, let's say, the way how we'll present it. It's not, let's say, you find in the book in this way, okay? So let's say going back and forth from, let's say, from a worksheet point of view, or let's say worldline or worksheet point of view, and the target space point of view, you will not find in many books. So I will introduce some ingredients that are very useful for if you want to study string field theory. So you know that recently, during the last 10 years, for example, there was a boost of studies in string field theory, okay? Because the string field theory, it's a way to go off shelf for strings, okay? Namely, you can compute the action for the strings, okay? And then you can study some dynamical processes. For example, the decay of D-branes can be studied in that framework. So you cannot study a decay of D-branes in the, let's say, in first quantized formalism. In the usual strings that we define in the book, you cannot describe really decay of D-branes, okay? But in the string field theory, you can describe decay of D-branes. And let's say in the year 2000, there was a conjecture by Ashok Sen that he conjectured, for example, the following: when you have an open string field theory, okay, then you have the presence of D-branes, because the open strings will attach to some D-branes, okay? Now, in open string field theory, there is a tachyon. You've seen there is a tachyon. I will show you the tachyon in this framework, how it emerges, and this is rather beautiful. Actually, there is a way to construct the string field theory action for the tachyon, okay? And then when actually there is a D-branes, which are unstable D-branes, and there is a tachyon, and there's two quantities they are going to let's say, to combine. Namely, if there is the tachyon, there is the tachyon is because there are unstable D-branes. So if the D-branes collapse, there is no tachyon, okay? And the way to check it is that you can check the energy of the tachyon against the tension of D-branes, okay? And then you can check if actually the two ingredients are equal, okay? At some point, of course, the way to do it using string field theory, because you really have to see in a string field theory what is the energy of this object, this extended object in string theory, and then you need an action for the tachyon to compute this effective action. Okay, and the way to do it, let's say 10 years ago, was actually to to do the mode expansion of your solution, and then compute this mode expansion in a rather painful way, because you have to reach to some level of your mode expansion and to do the calculation accurately enough to check actually if the tension of the brain was equal to the mass of the tachyon. Okay, and they did it, and they actually matched it to 99%. Okay, but recently, let's say in 2004, 2005, Martin Schnabel was able to construct an exact solution of string field theory, and then once you have an exact solution of string field theory, then you can really match, you can really check exactly if the energy of the solution really coincides with the energy of the brains, and then there is a complete proof of this conjecture. So let's say using string field theory, you can do these calculations. Okay, so of course I will not discuss the string field theory, but I will give you some ingredients how to do it string field theory in this framework. Okay, so let me start. Okay, so in the case of bosonic strings, okay, you have seen in the lecture by Carlo that at some point, in order to define the Hilbert space, you introduce some constraints. You require, for example, such a constraints on the vacuum equal to 0 and L0 minus 1. So these are the constraints that allow you to define the physical states in the Hilbert space in the case of strings. So those are constraints, okay? And actually, by using the Virasoro algebra, you immediately know that this operator would have only positive integers. In case they commute among themselves, okay? They also commute with L0 minus 1, okay? So the set of this generator here are commute set of generators. Okay. Now we'll study such a systems of constraints in the next lectures. But then I want to say, let's say, I want to rewrite this set of constraints in a kind of more, let's say, generic form, phi of a. Okay, phi of I, where I goes from 1 to n, let's say a finite number of constraints, okay, written in some coordinates. For example, suppose that I have some coordinates, let me call x the coordinate, or let's say the fields that I'm using to construct my model. Okay, it doesn't matter what are those fields. Okay, I have such a constraint, but for these constraints, which constraints means that this must be equal to 0. In this way, so namely, you construct your model, okay, you write down your equation of motion, and in terms of the fields of the model, or in terms of the Hilbert space, or the Hilbert states space, you impose a condition that your constraints are equal to 0 up to equation of motion eventually. Now, you know that you can impose a set of on your fields, on your theory, okay, only if those constraints satisfy the following equation. Phi k, okay, namely, where this bracket here is the Poisson bracket. Poisson bracket, okay. If I consider some quantized fields, this becomes, for example, the usual Heisenberg bracket. So there will be a Heisenberg bracket. But at the classical level, I can rewrite in terms of a Poisson bracket. So those are constraints on your theory, okay, on your theory. And if you calculate the Poisson bracket between the two of these constraints, okay, you end up with one additional constraint. Now, of course, it could happen two things, okay. It could happen two things. You start from a set of constraints, okay? You calculate the Poisson bracket among those constraints, okay? And it happens the following. Oh, it could be 0, okay? Could be equal to 0. So they commute, okay? Then I can impose, of course, I can impose simultaneously. If those two constraints commute, then I can impose those constraints on my Hilbert space simultaneously, okay? The second thing, they do not commute, okay, but they close their proportion again to some of these constraints. So they are linear combination of these constraints, okay? And those are called first-class constraints. First class constraints. First-class constraints. Namely, these constraints form a closed. The third case is that this is closed on some constraints, phi prime, okay, which is different from any of these constraints. Okay, so is a new additional constraint. Okay. There is even a fourth situation where this constraint gives you some C number. Okay. Okay. Let's consider the first case. If you are in such a situation, so the constraints commute, okay, it doesn't matter. So I can impose both constraints on your Hilbert space or on your physical fields, on your fields, okay, without any problem. Second case, suppose that they do not commute, but the Poisson bracket or the Heisenberg bracket, if you already have quantized fields, okay, they close again on some constraints. So they form a first-class constraints, okay? If this algebra is closed, namely any of those constraints, any bracket that they construct of those constraints close on one of them, namely they satisfy a Lie algebra of this type, where these are structure functions. Of course, if they form a Lie algebra, they will become a structure constant, okay? If they form an algebra, but this is not a Lie algebra, for example, in supergravity, discussed by Mario, for example, if you start to consider the constraints that you get in supergravity related to superdifferentialisms, okay, they do not close on a Lie algebra, but they construct on an algebra of this type where the functions are field-dependent structure constants, so they are structure functions, okay? But still the Poisson bracket of two generator, it closes on some constraints. So then automatically I can impose all of these constraints, because if we calculate the commutator between these constraints, okay, then I need that they close again on this constraint in such a way that I impose a consistent set of the constraints on my theory. Actually, there is a theorem which is called a Frobenius theorem, which tells you that indeed, if you have such an algebra, then this algebra is called a distribution, and is an integral distribution. It satisfies such an equation. Now, the third case is, for example, if they do not close an algebra, namely, if you generate a new constraint. Now, it happens. What you have to do? Well, you have to enlarge your space. You have to enlarge the space by adding these additional constraints. Compute all the bracket with the original constraints, okay? And then you must check again what happened. Namely, if the new algebra built with just the combination of the original constraint plus the new constraints, this could again satisfy the possibilities. Namely, if it is 0, so they commute with the rest, then you are done, okay? So you add these additional constraints, you check the compatibility with the rest. If this commutes, then you are done, fine, okay? Namely, the new set of constraints will form a maximal number of constraints, and then you can impose these constraints on your fields, okay? Now, if, however, it closes an algebra, then it's okay again, because it forms an algebra, then you can impose. If, however, it produces a new constraint, you have to do again the procedure. Namely, you have to add all these constraints, and you go on as long as actually you finish this line. Okay, so again, we have the following, the situation 0, phi k, phi prime, or a new one, phi second, and then you repeat. There is also another possibilities. For example, if these two constraints, they do commute to a C number, for example, okay? If they do commute to a C number, then if they do commute to a C number, this is not any longer a first class constraint, but it becomes a second class constraint. A second class constraints, okay, are more difficult to deal in the BRST framework. Okay, I will not do it now, okay, but at some point at the, I think in the fourth lectures, well, I will mention probably today, but then it will become important in the fourth lecture, and in the fifth lecture, second class you see formalisms, okay. Say this technique, you can find some books, but actually I never found in books, let's say, a useful treatment of these constraints. So when you have some second-class constraints which close on a sim number, or it close on some functions which is not a constraint, okay? And then, you see, the point is the following, okay? There is a huge literature about this how to impose the constraints. There are beautiful lectures by Dirac, okay? These are kind of really milestones, okay? You can read it and there is interesting things, okay? Then recently there are books. For example, there is a very good books by Mark Henault and Teitelbaum about the quantization of these systems and first class constraints, second class constraints. There is an analysis. However, when you have a second class constraints, okay, usually what the people does is the following. You try to solve it, or let's say you try to impose half of these constraints in order to solve part of the second class constraint. Namely, a second class constraint, it tells you the following, that the variables associated, let's say, if you have a constraint, okay, you can follow in this way. If you have a constraint, okay, it's just like as imposing a differential equations, okay? So you impose a differential equation on your fields, okay? Now, you can choose a set of coordinates in such a way that the constraints implies that there is an associated coordinate which disappear from your physical fields. Namely, it is like when you actually, in a Miltonian formalism, you choose exactly the coordinates which is related to a given constraints, okay? In such a way that you say, let's impose these constraints, let's choose a set of coordinates in such a way that the constraints implies that the coordinates is absent in your solution, okay? There is a relation in this way, okay? Now, second class constraint, you can solve it in this way, so just eliminated one of more coordinates. However, doing that, you breaking Lorentz invariance, you break the symmetry, the manifest symmetry of the theory, okay? Unfortunately, in old books, you always find that the second class constraints are understood in this way, okay? However, if you do it from the BRST point of view, okay, there is another solution. Namely, one solution is just eliminating some fields, okay? So eliminating some coordinates of your system. But there is another solution. You can impose some constraints on your Gauss field. So you have a constraints not on the physical fields of your theory, but you have constraints on the Gauss field. We will arrive at this point, but it's a completely novel way to do it, which has been done in 2000, so let's say less than 20 years ago, actually, this construction. So I will go back to this point in the last lectures. Yes, actually, you can do it also for central charges, for example. Okay, you can do it for central charges, and you can say, well, suppose that they want to impose some constraints which has. What should they do? Okay, and let's say in the case of Virasoro, okay, you can do it. It's rather easy to do it. Okay, but suppose that is not a number, really C number. Again, a C function, so it's a function of the fields, okay? So it seems that it likes that you generate new constraints. So you generate some combination of the fields that you want to impose on your physical fields, but you don't want to impose such as constraints on the physical fields, okay? And then, okay, how to do it's just a number, okay? But in not a C number, but a C function, okay? So a central charge, but which depends on your fields, okay? I will show you a very nice example where it happens, when it happens. Yes? You're right. No, in general, they are not constant, okay? In some simple models, they do form a Lie algebra, so the constraints form an algebra. But for example, if we consider supergravity, okay? Supergravity, you have the gauge symmetry related to the Fermions or super Fermions. And indeed, if you calculate the relation between the supersymmetry, the algebra of supergravity or the Fermions symmetry, they do not close like an algebra, so they are not numbers, but they are functions. Here. Well, okay, sure, you can. Can I redefine my constraint in such a way that it becomes a number? Yes. Yes. Yeah, of course you can do it, but then you run into the problem that your constraint becomes non-polynomial, okay? Or if, for example, it's very hard to define some constraints which are non-polynomial, for example. Of course, I will show you so in string theory that, okay, in Greenwich words, for example, you to problem where you have a structure function, okay? Then you say, okay, why don't divide by this function, okay? And then you immediately run into the problem because you get singularities of this function. If you have a polynomial, okay, you can deal with this. But you have a function, I don't think that anybody can do it in a very simple way. So the way that you suggest that you can reabsorb the structure function inside of the constraints, you run into problem that is non-polynomial or even a non-local. Well, sure. Constraints are polynomial in the fields and their derivatives, okay? Because actually you write down your theory in terms of polynomials and derivatives, okay? I mean, this is just a requirement on the locality of the theory. So if you have the theory, could depend supergravity in any dimension or in lower dimension like string theory. One of the requirements that the theories must be local, okay? And this locality requirement tells you that indeed these constraints are usually polynomial, okay? Then you start, then automatically you start here as something which is non-polynomial because I compute quadratic fractions, okay? So I will turn out to have some non-polynomial things. And then, okay, then you run into such problems, okay? So let's say the constraints let's say the hypothesis that I put on the theory, which is just a local, expressed on some polynomial of the fields. Of course, for example, supergravity, when you consider, for example, the couplings with the scalars, for example, you get non-polynomial, okay? But then you have other constraints, like, for example, holomorphicity in the fields. You have other constraints. Yes? Okay. Yes. 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 So let's say there are first-class constraints when at the end of this process, you end up with an algebra of this type, okay? So if they do form an algebra of this, okay, then you have a first-class constraints. If however, they do not form an algebra, because, okay, there are two ways they do not form an algebra. First is just a C number, okay? Then it's not a constraints at all. Or the constraint that you don't want to add to the set of constraints, okay? You don't want to have such a situation, then you end up with second-class constraints. Okay? Okay, let me go now one step more. So now, how can I do with this object? Okay, so let me try to do the following. Okay, so once I have this one, let's say I will deal with this case for the moment. Okay. When I deal with this case, okay, let me do it the following. Now I introduce a set of fields, I will call Gauss fields, okay, in this way, C and Bi. So I will call it like C and Bi, and those are anticommutative fields. So if I calculate, for example, the anticommutator between these two, Cj, this is equal to 0. Or I can rewrite also Ci, Cj plus Cj Ci is equal to 0. The same it happens also for B, Bi Bj, this is equal to 0. But if I calculate the Ci Bj plus Bj Ci, this is equal to delta Ij. I and j runs from 1 to n. Okay? Good. Now, using this quantity, I can do the following. Okay, I built an object which going to call Q, which has the following expressions: Ci phi I. This is just the first term. Okay, then I will add some additional terms here. Okay, and then I do the following: I compute the anticommutational relation between Q and Q. I compute the anticommutators in this. Okay, so if you do the calculation, is the following: Ci phi I. This is just the Poisson bracket, or if you, it depends if you have a classical field or if you have a quantum field. So if you have quantum fields, this is just the anticommutator to be intended as the anticommutator between fields. Okay, Cj phi j. I always assume that the same index means summed index in this way. So you see that here in this equation, it appears only the, okay, because it means the following. Let me do it in this way. Ci phi I times Cj phi j minus Cj phi j Ci phi I. Now, you see, this quantity here, I can bring it here, and also this quantity here, I can bring it here. Okay? Then I can rewrite this expression in this way: Ci Cj phi I phi j. Okay? Then, sorry, here I have a plus. Okay? I have a plus. Okay? So I get a Cj Ci phi j and phi I. Now I used this formula here. I used this formula to exchange these two quantities here. Okay, and if I use this formula and exchange it, I bring it in front, so I get the Ci Cj times here I have phi I phi j minus phi j phi I. So here I'm reconstructing. Let me cancel this. Okay, so here, this equation QQ gives you what? Gives you Ci Cj times here the commutational relation between these constraints. So I can rewrite this expression using the algebra. So Fij k phi k. Okay, so this means the algebra. So the Q operator. Okay, the Q operators, okay, the anticommutator with Q with itself, okay, is not 0, but you see it closes in this way, okay, it gives you something which is again proportional of the constraints, okay. So then you can do the following, you can add here, in additional terms of this type 1/2 Ci Cj phi I j k bk. I can add an additional terms of this type, okay, such a way that in such a way that when I calculate the Q with itself, okay, with Q, I have the following. So I write schematically times C phi times CCB, okay, in this way. So you see I have the commutational relation between these two pieces, okay, which is just what I give you, C f and phi. Then I have the commutational relation between this and this, okay? You see, but when I calculate the commutational relation with these two pieces, okay, it turns out the following, that the CSC with C anti-commutes, okay, so I don't get anything. But here I have a B with the C, okay? But B at C, just remember that B I at C j gives you just the delta function, delta ij, okay? This gives you an additional terms, which gives you exactly, so if you do calculation, gives you minus, okay, and then you get a CCF of phi. I will just leave you as an exercise to compute by yourself that gives you exactly this minus sign, okay. Now, of course, I have this term with these terms, which gives you this term. Good. Then I have these terms with this one, but I also have these terms with this one, okay? So this is the reason why here I get this funny factor half, okay? This funny factor half here, which I put in front here, it is needed because I have two objects, which is this one with this one, and this commutational relation with this one. So this gives you this factor 2, which cancels this factor half, okay? But then I'm left with this, with this. So I'm left with the last ingredient, which is this one and this one. And this gives you another terms, okay? Another terms which contains, you see, here there is an f. Let me put also the f here, schematically, in this way. So, you see, this B could act on this C and this C. And this B could act on this C and this C, okay? If you do the calculation, you get something like a 1/4, okay? And then you get something like a C B times, because one B removes one C, the other B removes the other C. So at the end of the day, actually, the B removes one of the C here, and the other B removes one of the C, so you end up with the CC times 2 Fs. 2 Fs, okay? Now, if you write down this expression, okay, with the indices, okay, and you compute all the expression, you see, this minus sign is going to cancel this expression here, but you are left with this expression here, okay? Now, if you calculate correctly this expression, it turns out the following, that this expression here, written with the indices, has the following expression, Fjk, Flkm, plus, now here I keep one fixed, okay, and rotate the other one, Fi, Lk, F, let me see. Okay, let me write down this way. Okay, I have to rotate this one, so J, this is L, so I have a K, I, M, times F, here will be K, I, F, no, K is not, is just L, I, J, M is equal to 0. So, namely, because of the antisymmetrization of this quantity Ci, okay, here, okay, this quantity here, okay, you see there will be this quantity here, and there, because of the antisymmetrization of the C, okay, you end up with an expression of this type, okay, where these three quantities here, I, J, and K, are cyclically permuted, okay. Now, and this is 0 by Jacobi identity. By Jacobi identity, there is. Okay. Now, okay. If this is, okay, if you started from this quantity here, okay, in order that this is just a formal algebra, a Lie algebra, okay, then of course I have to derive what are the constraints of this Fijk, okay. In the case of supergravity, or let's say for supersymmetric model or Yang-Mills theory, this is just a Lie algebra. In the case of supergravity, this is not a Lie algebra, but it's an open algebra, okay. Then, okay, in that case, I have to do something more, okay, in order to deal with this object. With I have structure functions, I have to do something more. Namely, what I have to do, actually, I have to add the additional pieces in order to compensate the presence of structure functions, okay. Okay, so we end up with the following quantities: q square, or let's say the anticommutator between q and q is equal to 0. Okay, so this operator here, it is nilpotent. It is a nilpotent operator, okay, written in terms of the fields. Written in terms, written in terms of the fields, I can compute q acting on phi I. If I compute the acting phi I, this gives you some fi j k cj phi k. Okay, q acting on bi, this gives you phi I times f I j k b k c j, acting on q on ci is equal to half of f j k I c j c k. So acting on the fields, okay. Now this is, so this piece here is quite important, because you see that the commutation relation between the q with the, just only two things. Okay. I always use a commutation ratio written in this way. So if you're using Poisson bracket, I use this curve bracket here. Starting from now, always use this square, okay. Now, this is a commuting quantity, anti-commuting charge. And the reason is the following. You see, it is built in this way. So these are commuting quantities. So these are commuting, let's say, they are bosonic constraints. Bosonic constraints. And then for that, I've chosen these anti-commuting fields. So Ci and Bk, those are anti-commuting fields. Okay. So this means that this bracket here, fermion and a bosonic quantity, so it is just a usual commutation relations. So an anti-commuting quantity times a bosonic quantity, so a commuting quantity, gives you again something which is anti-commuting, because this is anti-commuting and this is commuting quantity, or let's say bosonic and fermionic. Let me use these words, okay? Now here in this case I have an fermionic charge times a fermionic fields, okay? And this quantity, this is not just a bracket, but is an anti-bracket, or let's say an anti-commutator. In this, let me put plus if you want to. And this also, let me put a plus again here in order to have an anti-commutator. And you see that a fermionic quantity times a fermionic quantity gives you bosonic here, and also this is a bosonic quantity. It's just a product of two fermionic quantities, and gives you again a bosonic quantity in this way. Now for what's concerned the C, again here this is anti-commuting, this is fermionic, and this gives you product to fermionic quantity, which is again a bosonic. Now you see that this relation here tells you that the BRC transformations of the big ghost gives you echo strains pieces coming from the Gauss fields, okay, times a piece of Gauss fields. So essentially, I'm able to read the constraints of your theory just by projecting on the Gauss fields in this way. Okay, one fast way to check the nilpotency, instead of using this technique by using one way to check the nilpotency of these relations is just by computing the BRC charge of this quantity, for example, of this expression. So this is a fermionic quantity, so I will have something like a Q times phi r. Okay, and then I have to compute what is the Q of phi I j k, Cj fi k. And then I use the fact that this is just derivation, so a derivation will act on this ingredient. Now, if I suppose that the Fij are constant for the moment, okay, if they are not constant, I will have to add additional terms, but I will not do it in these lectures. So I suppose that for the moment these are. So if I act with the QBRST on this expression, this act with C and act Q on phi, and if I do the calculation, it turns out that you can easily prove this is 0 again by Jacobi identity. By Jacobi identity, this is equal to 0 again. In the same way, you can easily check this expression. One easy way to also to deal with this, okay, which is rather simple. You see, view it in this way, okay. I can do the following, okay. I can translate as a dictionary. In this way, Q, I read it as a differential D. Okay. A field phi I, let me read it as a form phi. Also Ci, let me put like a C, and Bi, let me call it B. Okay, and then I can retranslate this expression in the following way. D of phi gives you, and then this I rewrite in this way, like a C wedge phi, with a wedge product. Let's say, if I express this equation in component, I am back to this expression here, okay? Let's say I can rewrite formally this equation in this way, okay. The second equation, let's say this one, d of c is equal to half of c wedge c. And then this one, d of b, I can write as a phi times what I wrote it, c wedge b. Okay. Now, independently of the indices, okay. So independent of the indices that I wrote here, okay. I just translated. I just used just a simple dictionary to translate these equations in the following expression here, okay, where I rewrote this structure constant here as a wedge product, okay. Now, these equations are rather familiar, actually, because you can view it in several ways. For example, let me write down for you a set of equations which are very similar. Suppose that you look at these two equations here. Which kind of equation this remind you? You have ever seen an equation like this? These two equations here? Suppose that well, they are Murray-Cartan. For example, suppose that I take a Firmine for a space and a spin connection. Okay, so let me write down the torsion. The torsion is just dE minus omega wedge E. Okay, and the curvature, for example, R, is just d omega minus omega wedge omega. Okay. Now you see, this equation really resembles this expression here, for example. Or, for example, if you, and these are generalization of the Murray-Cartan, for example. Well, a Murray-Cartan usually are obtained only for just for a curvature. So suppose that the omega is just E plus omega, for example. Okay, and you write down Murray-Cartan for this expression, for example, and then you decompose in this way, you get just a torsion and thus a curvature. Okay. So this means the nilpotency of these systems. Okay, you see, in this way, I just ask that the torsion is 0 and the curvature is 0, for example. Okay, and so if the torsion is 0, okay. Now, of course, if you calculate, for example, the nilpotency of these systems, because d square is equal to 0, then you end up with the Bianchi identities. So you get a dt plus omega wedge t is equal to 0, and the d of r plus omega wedge r plus r wedge omega is equal to 0. Okay? So these are the Bianchi identities. Bianchi identities for the curvature. Now, of course, if I set this equal to 0, then the Bianchi identity automatically satisfied. Okay? And let's say, setting to 0 and then using the nilpotency of the differential, it is just like write down this set of equation where differential d is nilpotent. Okay, and yes? Well, yes, okay, here there is no half in this equation, okay. In this one, you mean? Wait. Yeah, it depends if I write down as a commutator, okay, or if I write down with just a wedge product, okay. I can write with a half. For example, right. If I write in this way, I should put a half also here, like the field strength of Jan Mills. I should put an half here. Yes. Usually I write, let's say for the curvature, I write using the index, so it's easier, okay? If you write down as a form, but which is also a matrix in the tangent space, then automatically you can put in half, yes. Okay, so in this way, essentially, the BRST operator that I constructed in this way, it is rather a very generic operation, actually, and you can use it in several frameworks. For example, for topological theories or for strings and so on. Okay, and using this equation, it's rather easy to check that it is automatically nilpotent. Okay, let's see. This translation usually it's rather easy in order to let's say to check the nilpotency of the BRST operators and to do some calculations. Okay. Now, the space of my fields now in this case are the following. We have a space of the fields which are just some fields axes which are the coordinate on which I wrote down the constraints. So the constraints I wrote in terms of some coordinates which are fields, for example, if I consider some quantum field theory, okay? So some coordinates. So I will have some ghosts, Ci and Bj. So this is the space of the fields that I'm considering here. And now I want to construct out of the space of the fields a specific space, okay? Because I can act, once I have any polynomials of these fields and derivatives of these fields, okay, then I can act with this operator here on omega mapping into omega. So namely, this operation here which will be only polynomial operation, so I act Q on these fields, on let's say on any combination of the fields on in polynomials, I get back to the same space. Now of course, if I try to compute something in this space, it is rather complicated. Okay. However, once I introduce these fields in the way that I did it, namely the anticommute, let me use again Cj plus is equal to 0, Bi Bj plus is equal to 0, and Ci Bj plus is equal to delta Ij. I can do the following. I can introduce a new charge, which is called Faddeev-Popov charge, which I can write down in this way, BiCi. Now, if this charge act on any field axis, okay, any field axis, this gives you 0. So the field axis do not carry any charge. If I calculate the q phi pi acting on Ci, this gives you Ci. And if I act with the q phi pi acting on Bi, this gives you minus Bi. So this means that these fields here, all the fields that I'm starting with, okay, have Gauss number 0. Okay, so this charge is called Gauss charge. And it gives the following. So this is just the charge. So the field axis have 0 charge. The field Ci gives you plus 1 charge. The field Bi gives you minus 1. Minus 1. So you see that the BRST operator here Now, this quantity here, which are the constraints in terms of the fields X, they have Gauss number 0, Gauss charge 0. This quantity here, which is a Gauss, has Gauss number plus 1. This quantity here, so is plus 1, and this gives you minus 1, it gives you plus 1. So the two pieces of the BRST charge, this one have the same charge. In total, this quantity has 1. So in this table here, I will also put the BRST charge, which has charge plus 1. Now, so the fact that the Q has a Gauss charge plus 1, mathematically I can represent in this way. If I calculate q phi on q, so if you calculate the computational relation between this charge and this charge, this gives you q. So the BRST charge has charge, Gauss charge equal to plus 1. So this means that if I take this space omega and I decompose the space and in terms of spaces, which depends on the coordinates, field C and B, okay, in such a way that those spaces are eigenspaces with respect to the charge. Normally, each spaces carry a specific Gauss charge. Gauss charge 0, 1, 2, 3, and 4, and so on. Or also negative, because you see, I can also go negative with the charge by adding more B fields. Okay. It turns out that the BRST charge Q map omega n into omega n plus 1. Okay, so you see, this okay, is very similar to what happened with the differential D. The differential D maps a P forms into omega P plus 1 forms. Okay, so the Gauss charge is very similar to the form degree. Okay, the form degree, okay, it is increased by the BRST operator. So the differential increases the form degree in the same way as the BRST charge increases the Gauss charge. This is an analogy which is also very useful in a lot of applications. Second thing is the following. The BRST operator is nilpotent as it is the differential D. Okay, the differential D is nilpotent. The BRST operator is also nilpotent. So this means the following. If I consider an equation of this type, Q on even some omega gives you 0. Okay, so I use the same language, the same dictionary, I would say that this object here, this operator omega n, it is closed. It is BRST closed. BRST closed. And of course, this equation has a very simple solution. Omega n equal to q on eta n minus 1. By the way, okay, sometimes I use the notation, this notation, namely, if I want to act with the BRST charge on the fields, I use the notation with the bracket, okay? Sometimes you will see that I have a notation like this, Q acting omega, okay? Now, this view is just a view as a derivation, as a derivative, okay? Indeed, actually, this is an anti-derivation, because it's an anti-commuting, a fermionic operator, okay? So when you see it just attached by this expression, I just mean that it's just a derivation. I will use it as a derivation. But of course, this expression here, it is exactly equal to Q acting on omega n. Okay, just only for brevity, I write down in this way. So also this one is equal to Q of eta n minus 1. The only difference is that I don't have to bother if it is just a commutator or anticommutator. Just write down as the derivation. And if this quantity is anti-commuting, I just have an anti-commuting quantity and so on. So I don't have any problem here. Let's say Q, it is an anti-derivation. Okay? So and then I can work with that. Now, of course, if omega can be written in this way, then this automatically satisfies such an equation. Okay, there is two ways to see it. One way is just using derivations. So Q of eta of n minus 1. This gives you Q square acting on n minus 1. This view Q as a derivation or anti-derivation, and this is automatically 0. Or if you want to do it with the commutators, so Q on eta n minus 1. Okay, then you can use the Jacobi identities. Okay, then you use the Jacobi identity. But since this is the same operator, which is the same operator, and there is an anticommutational relation, this you can rewrite as minus half of Q acting on eta n minus 1. Okay, in this way. And then you use the fact that the Q square is equal to 0, or Q anticommute with itself. So this is 0. Okay, so you can do it in the same way. Okay, so if this operator here is written in this way, then you say that this quantity here is exact. Okay, I use the same language as in the case of differential geometry using forms. Then automatically there is a nice set of operators, which is the following. So I can construct this quantity omega hn, which is just written in terms of the space omega, which is just what? It's just the space of omega n, such way that the Q on omega n is equal to 0, okay, divided by those omega n minus 1, by omega n, such way that omega n is written as Q of n minus 1. This is called the n cohomology space of Q. So this is the n cohomology, or the cohomology at n Gauss number of the BRST operator. Okay. Okay, so I just used the same, exactly the same. I just translated in this language what I know from usual differential geometry. In usual differential geometry, you know that we will call it the RAM cohomology of your space. Okay, this is just the BRST cohomology. In the usual differential geometry, I have the P form, the P num, the form number, and that's actually filter my space with respect to this number here. And in this case, I have the Gauss number. Pay attention that in the case of normal differential geometry, I will have only positive or zero positive degree forms. Here I could have also negative form, negative degree, because I can have negative Gauss number. Okay, this is a funny story I will tell you. Namely, usually in geometry, you have only, as I said, a positive, let's say, non-negative form degree. Indeed, actually, if you consider super geometry, namely, if you consider not only a manifold which has a bosonic coordinate, but even fermionic coordinates, then automatically you can get also a negative form degree. Okay, and in string theory, for example, you also have a negative form degree because of these Gauss numbers. Okay. So let's say the study of this cohomology is rather important, and I will show you why. Okay. However, I want to do a little more things, which is the following. Now, you see, this space it is filtered with respect to this number, okay, and actually it is easy to construct an index, which is defined in this way. It's just a sum of P is to 0, okay, of the following: P of P times the dimension of HP of omega. Okay, so this is let me write down in this way. This is called a Poincaré polynomial. Okay, namely, I sum up, okay, the dimensions. So here I count just the elements of the spaces, okay, and then once I counted, so I just computed the dimension of the spaces, I just multiply by TP, okay, and then I can write down a polynomial. So this is just a polynomial. And now this polynomial is quite important, because this allows me to do the following: to count of this type. It could be anything. Okay, it could be 0. Okay, it could be 0. Okay, could be just a finite polynomial. Okay, it could be also infinity. There are cases also is an infinite number. However, this is not really an index written like this. Okay, because you see, essentially, it is difficult that it becomes 0, because all the spaces must be 0 in some sense. Okay, in order that this is 0. Of the spaces must be 0 in order that this is 0. Okay. However, there is another way to write down. Okay. This is known as a Poincaré polynomial, but actually there is really an index following sum of P to Z, and then here put also -1 P of TP of dimension of HP. Okay. Now this is it's more like an index, okay? It's more like, because of this minus sign here. Because of this minus sign, okay. Suppose that, for example, that I have two spaces, H0. Let me do a more realistic one, H1 and H2. Okay, two spaces like this. Suppose that the dimension of these spaces is equal. Okay, then this expression here becomes exactly like this. Is equal to when P is equal to 1. This gives T, and then they get the dimension H 1, and then in the second terms plus, so minus 1 to the square, t square, dimension of H2. But they are equal, so let me put it just like this. And then if I write down this expression, it turns out this expression is just equal minus, then let me collect the t, 1 minus t, and then this is just the dimension of H1. Okay. Now you see the following. Okay, this is a character in this way, but then if I take the limit, t gives you goes to 1. Okay, this let me call it I don't know, chi of t. This gives you 0. Okay. Now this expression here, it is just partition function, for example, in the case of a tachyon, for example, in the case of a tachyon, where actually you get the two states. Okay, I will show later how this comes out. So the fact that there is a minus sign here, okay, this makes it not really a character, but it really becomes a let's say an index function in this way. Yes? Okay, an index, well, an index is a, okay, there are several ways to define an index, okay? Usually an index is just a quantity, okay, is just a number, or in this case is even a polynomial, okay, which is a invariant deformation, namely if I change the space, okay, if I do deform the space, this index remains the same. Okay, this is just one way of defining. There are several indexes, for example. The partition function, well, usually is not an index, but the partition function for supersymmetric theories, for superstrings, it is an index, okay? And then in particular case, t equal to 1 is just the supersymmetric point of the theory. I will show you how this works in a completely way. Yeah? Okay. Okay, let me do it and do an example now. Okay. Yes? It equal to 0, okay, because the two spaces are equal. Okay, the two spaces are equal. You see that I get this factor 1 minus t, okay? And then for 1 minus t, that this becomes 0, okay? Now, this is very important for an index when at equal to 0, it gives you 0, okay? In such a way, the index, okay, this essentially tells you that there is a duality between these spaces. And this 1 minus t, okay, allows to implement this such a duality. Let me try to tell you in a different way. Okay, when t equal to 0, so because of this quantity it gets 0, okay, this tells you essentially that there are spaces, okay, where actually the dimensions are equal, okay, but let's say the two spaces at h1 and H2, okay, are two spaces which have different Gauss number, okay. So this is if this is a bosonic operator, those are fermionic operator here. So this means when you take it equal to 0, the fact that this quantity here vanishes means that there is a matching between the bosonic quantity and the fermionic quantity. So the fact that the given index t goes to 1 gives you 0, it is just a signal that you have a supersymmetric balancing between fermionic and bosonic fields, okay, and that there is such a cancellations, okay. Well, equal 0, it's a different story, because here I've chosen just these two spaces. For example, if I have, for example, H naught, just only the first spaces, for example, then this gives you just the 1 here. It is not 0. Okay. So, for example, in the bosonic strings, it happens that for the tachyon you have such an expression. For example, if you consider the first massive states, okay, the expression will be different. Okay, and then you also have the constant here, but just multiplied by 1 minus t in front. Okay. let's say, it's a very useful way. So if you, sometimes you can easily compute this expression here instead of computing exactly this, the dimension of the spaces, okay? And then if you are able to compute such a quantity here, then you can check if there is a supersymmetry or not in these spaces. Yes?
If we consider that omega spaces, geometrical spaces,
Right. This counts.
is there some significance of the fact that one is just the Euler characteristic?
Yeah, I mean, this is exactly, in the case of usual geometric things, it's just the RAM operator. This gives you the sum of Betty numbers, just weighted with the minus sign. This gives you just a Euler characteristic. It's exactly the same. I mean, this isn't just an index. It's the Riemann-Roch theorem that gives you that, right? Okay, let me show you an example. I will show you, well, probably today 2 examples and tomorrow an additional examples. Let me consider the following. Okay. Okay, let's consider the following example. Okay, I consider the following action S, which is just the integral of tau of p. Let me write down p mu x. So derivative of x mu respect to d tau plus half e of p mu g mu p nu. Now, where x mu is just a field which depends on this parameter t. So this is just a word line. Okay, t is the word line parameter. So I'm considering just a line here, just a word line parameter of a point. Moving in space, okay. Mu is again a field. Now, E is a field which is called an Einbein. Okay, so here there is only one single Vielbein, which is an Einbein. Okay, and the G mu nu, I take it constant metric on the target space M. Okay, so let's write down the equation of motion of this model. Okay, let me write down the equation of motion of this model. Okay, first of all, let me write down the equation of motion for P. Okay, just derive the Euler-Lagrangian equation of motion of this model. If I take the equation of motion for P, I get dx mu of d tau plus E P, so it is P, I will, because this is a constant, if I have a P mu, G mu nu, like a P nu with just an index. So I use this constant G mu nu to raise to lower the indexes. So here I have this expression here. So P mu, I write down as a minus 1 over E of dx mu of d tau. Now, of course, if I use this solution for P mu, if I plug back here, okay, I get what is called a differential, a diffeomorphism invariant or reparameterization invariant massless point particle. So it is a massless point particle moving in d dimensions. Moving in d dimensions. So this is the first equation. The second equation is just the derivative with respect to x, which gives you p mu So sorry, derivative of p mu respect to tau is equal to 0. Now, this equation here, if I apply this to this equation, okay, I will get, well, a derivative of E, okay, a derivative of E, and then I have a derivative on these terms, okay, on these terms. So I will get a minus, so plus 1 over E square, derivative of E respect to tau, dx mu respect to d tau, okay, and then and then I have to take a derivative, second derivative, which is just minus 1 over E, second derivative x mu respect to d tau is equal to 0. These are the geodesic equations. Geodesic equation for x mu. Yes, and what else? Yes, and then I still have one equation for E. Okay, if I equation motion for E, I get a third equation which is just the p mu is equal to 0. So you see these two equations here, this equation here are dynamical equation which takes the derivative with respect to tau, the parameter. This is non-dynamical equations, which is just an algebraic equations. Okay, so this is a constraint. A constraint. Okay. Okay. So then I can do the following. Let me do the following. Okay. One way to study this model, okay, is the following. So if I look at this expression here, okay, because of this constraint, essentially, I can say, well, this model here has symmetry, which is the following symmetry, which is just the diffeomorphism invariant, or let's say reparametrization invariance. Let me show you. So I have this variation, which is just let me call, how I call it. Yes, it is just d tau, and let me equal to 0. Let me check if this action is invariant to such other parameterizations. Okay, if I do just a variation, okay, I have a variation of p gives you 0. Sorry, I'm sorry. Here I put just so this is a p mu. Okay, let me use this. Okay, if I do the variation of this, it gives you p mu, then a d of tau, c of p mu, plus 1 over half the variation of E, okay, and then I have a p mu. Let's check this expression here. So of course this everything is integrated. Then this gives you what? This gives you. So if I do the calculation, I can do the calculation this way. First I will do partial integrations. So I get minus derivative of p mu down respect to the tau, c p mu. Then I can rewrite this expression in the following way. It's minus c derivative with respect to tau of p squared over 2. And then finally I will do partial integration again. So I get the derivative of c with respect to the tau of p squared over 2. So the variation of the first term, I just rewrite this here. The variation of the first term gives you derivative of c respect to d tau, p squared over 2, times plus 1 over half of d of e of p mu. Okay. Now this equation tells me that the variation of E must be equal to minus derivative of psi respect to d tau. Okay, so this action here is invariant under such a symmetry. So this is a reparameterization invariance on the line. So I'm reparameterizing the line, and the action is invariant. Now, since I have such a symmetry, okay, I can use this gauge parameter. Can use this gauge parameter in order to set E equal to 1. Okay, so this is just the gauge fixing. Okay, so I will do this gauge fixing here. I put E equal to 1. So the action will be the same, but with the fact that E equal to 1. So if E is equal to 1 is a constant, okay, so this equation here, the equation of motion here, this part of the geodesic becomes 0. Okay, this term becomes 0. And then I get the following equation. X, let's say, the second derivative of dt mu in the tau is equal to 0. Derivative of p mu in the tau is equal to 0. And E is equal to 1. Okay. Now here I can easily compute it. So P mu, now I can write as a P mu, which is just a constant parameter P mu. It's a constant, P mu is a constant in this way. And X mu I can also solve. X mu I can write down as X0 mu, which is just a constant, plus tau P mu. So this is second derivative of x must be equal to 0. Okay, second derivative of x must be equal to 0. And then I can solve these equations. Okay, and then I use also this equation here. So you see, the derivative, so probably I should put a minus sign here. Okay, in this way. In such a way that the first derivative satisfies this equation here. P mu is a constant. This equation tells me that the P mu is a constant. So P mu is a constant. I will call it this constant P mu. Okay. And then this object here is just a constant P mu. So in this way I solve the equation of motion. Well, this is a rather simple way. Okay. And then finally I quantize it. So to quantize this here, I just impose these are not just the fields, so are not a number, but they become operators. So I have a P mu x nu 0 is equal to delta mu nu. I put an I also in order to preserve the hermeticity. So they satisfy such a commutational relation. These are Heisenberg commutational relations. Okay? So I quantize it in this way. So the Hilbert space, for example, the Hilbert space, now the Hilbert space I can define in this way. Any states I can define as a function of x naught. Okay. Of course, the x naught, these coordinates commute among themselves as an operator on the Hilbert space. They do not commute with P, but they commute among themselves. So I choose just a set of the commuting variables to quantize it. Okay. I write down just the wave function. So this is the wave functions. Okay. So this is a vacuum. Okay, and the vacuum, and this is just a function of x naught in this way. So I just choose this Hilbert space. But do you remember that we still have one equation of motion to solve? So we solve the equation of motion for x dot mu equal to 0. We solve the equation of motion P mu is equal to 0. But we still have one equation of motion which is P mu equal to 0. Okay? This I have to solve it. But actually we solve it just by imposing such a constraints on the physical states. Okay, we impose such constraints on the physical states. Okay. So if you impose such a constraint in the physical states, okay, so P is just the P mu acting on this space. I just use these rules, and what I get here? I get the following, okay? I get that the second derivative, so d mu, acting on this function x naught is equal to 0. So this is just the Hamiltonian constraints. It is translated into just the Klein-Gordon equation. Klein-Gordon equation of this function here. Good. Okay, so this particle here is describing really a massless relativistic particles in the dimensions. Okay, okay, fine. Okay, here if I want to do interactions, so I will probably have to introduce a potential. So I can do several things, but I'm not going to do it now. Okay. Now, what I want to do is the following. So now these are my constraints. So these are the constraints that we were discussing before. Of course, here I have one single constraint. Okay. Let me do the following. So let me do the BRST charge. So in order to do BRST charge, I should have two ghosts, C and B. Two ghosts, and they satisfy again the commutation relation CB equal to 1, C anticommute with itself, and B anticommute with itself. So the BRST operator Q is equal to C P square. Yeah, P square, like this. It's just the ghost times the constraints. Now, in this case, I don't have to do nothing more, because Q with the Q, that's easy, because I have a C P square times C P square. Now, P commute with itself, C anti-commute with itself, this automatically gives you 0. Now, let me write down. Now I have to say, okay, what is now the Hilbert space? Okay, now the Hilbert space that I'm going to use now is the following. Okay, so here you see the Hilbert space I choose here. I've chosen here for discussing this in this framework. I just consider the maximum set of commuting variables, so x naught here. Now here, I also need a maximal set of commuting variables. So my Hilbert space, this omega that I was discussing before, is just made of x naught mu, and the ghost, I just choose the ghost C, okay? Then, of course, these spaces can also be filtered with respect to the ghost number, okay? Now, since here, ghost number, let's say the Hilbert space contain either these bosonic variables and this fermionic variable. This object could have only the following two terms, omega 0 plus omega 1, okay? Namely, omega 0 corresponds to any function of x naught. Omega 1 corresponds to any function g of x naught times c. Because the c square, remember, c square is equal to 0. So any cn is equal to 0. So it is a Grassmann quantity, a fermionic quantity, such a way that the c square is equal to 0. So my full space is made of two ingredients here. Yes? Yes, because you see, my field space, I choose maximal set of commuting variables, okay? Maximal space of commuting variables are the bosonic variable x naught mu and the anti-commuting variable c. Of course, I've chosen also b instead of c. Okay, one choice is this one. Good. I choose this one, okay? Now, you see, I can construct any expression of this quantity here. Look, okay, this quantity is constant, constant operator. Also, this I chosen constant here. I don't care for the moment. The fact that they could be depending on tau. I choose just constant for the moment. So any operator that I can write down are of this form: either a function of x naught or a function of x naught times c. I cannot write anything else. So my space automatically split into spaces, omega 0 and omega 1. Okay? Let's now compute the BRST cohomology. Okay, any element of this space omega, here, let me write down these spaces in terms as a function of x naught plus a function of g x naught times c. Okay, this is in differential geometry is called a generalized form. Is an element of the exterior algebra. Okay, it's just a generalized form with all the possible degree form. Okay, I'll do it in this way. Okay, I put also the vacuum here in order to be clear. Let me act with q on omega. Q omega. When I apply the QBRST operator, which actually I erase it, maybe I can rewrite here. CP square. When I act this operator on these spaces, here I get to this terms, which is just a C, okay? And then when I act with P, this gives just the Laplacian, acting on function x naught. On vacuum, but the second terms here gives you 0 because there's already c square gives you 0. So when I act with q on this quantity here, I don't get anything. Okay. So a closed form, okay, a BRST closed form implies that the d mu c mu of phi of x naught is equal to 0. But no condition on g x naught. Okay? So a generic form, a generic element of the spaces, it is naturally decomposed into parts, omega 0 and omega 1. Okay, and then I rewrote in this way: f of x naught times g naught x naught and times c. Okay, I decompose in this way. I act on the BRST operator on this. I require that this is closed. I find out just the same differential equation that I was getting here. So this function here satisfies the Laplacian equal to 0, but I don't get any condition on g naught. Okay, so if I require that this is just a close of quantities, I get just the correct equation for f, but no equation for g naught. However, I have to remember that this quantity, in order to be a physical quantity, must be in the cohomology. So the cohomology, okay, must be identified with the physical fields. Let me check now what happens if I say omega must be equal to q of something. Of course, this quantity here, okay, is again in the same space. So this means acting on something which is, let me call it eta, so let me call it lambda of x naught plus, rho of x naught times c. Again. So also eta here, I decompose in these two elements here. When I act with q, you see, the first one produces exactly c of Laplacian of lambda x naught, and the other one produces nothing. Okay, so you immediately see that if this quantity here must be in the cohomology, I get one condition on f naught, okay, which is just the Laplacian. And you see, the second condition, it tells me that you see that you get something which is proportional to c. If this is in the cohomology, I should not be able to remove, or let's say, this quantity here should not be exact. In order to be exact, this cannot be expressed in terms of the Laplacian of lambda. Okay, so this means the following: that this is just a physical quantity if and only if the lambda is not in the kernel of the Laplacian. Right? So this means the following. So the cohomology H naught on the space, okay, is just the function f x naught, okay, such way that Laplacian f is equal to 0, okay? And the space of H1, x0 and c, are the function g, such a way that the variation of g is something which is not lambda or something. Okay. So this means the dimension of H0 is equal to the dimension of H1. And both contain the same homology. Both contain the same homology. Namely, it contains this homology because this tells you that it's true for any function which is not in the kernel of Laplacian. Okay. So the dimension of H, the dimension of H1 is equal, okay, and then I can write down. I can write down the index in this case. The index in this case is just okay. So it's just 1, okay, which counts these states, okay. Times. Well, times, let's say, times the number of harmonic forms on my space, for example. Times the number, let's say, times the number of harmonic forms minus t, okay, and then again the dimension of H1, which is the same. Number of harmonic forms. So this is equal to 1 minus t, and then again number of harmonic forms. Okay. So this shows you these techniques. Let's say the heuristic homology, okay, reproduce exactly the physical space, namely the harmonic forms on this manifold. Let's say on d-dimensional manifolds, the harmonic forms on d-dimensional manifolds. But in addition, there is also another space, okay, which is the space of the harmonic forms times this Gauss C. Okay, so there is a duplication of the cohomology here. Okay, a duplication of the cohomology. You can read it also from a supersymmetry point of view. Let's say there is just one cohomology which is made of this function here, and one cohomology made of this function here multiplied by the Gauss C. Okay, there is a duplication of the cohomology. This is a phenomenon which happens in all string models. Okay, in all string models here. This is one thing I want to tell you. So for t equal to 1, this gives you 0, which actually the two spaces are indeed equal. Okay, this is first things. Okay. Yes. Okay. I will stop here, okay. Tomorrow I will show you that using this technique, okay, I will derive the target space theory. As a string field theory model. Yeah, I will stop here because tomorrow I will try to convince you that I'm not only able to get the correct physical space or the correct equation of motion, but I can also construct using this technique the target space theory. Okay, okay. So the Lagrangian for the fields, not the Lagrangian for the point. Okay. Thank you.